You give a local AI agent access to your system to help write some code. 10 seconds later, a single poorly constructed remove command triggers automatically, and your entire home directory is just completely gone. If you are building AI applications by yourself, you live with a constant, uncomfortable trade-off. You want the speed of letting an agent interact directly with your file system, but you cannot afford to lose the very machine you rely on to do the work. That tension spikes when you are working on high-end hardware, like an NVIDIA DGX Spark. This single machine holds your credentials, your work-in-progress drafts, and your web browser profiles. You don't have the luxury of spinning up a fresh, disposable virtual machine for every new experiment. The machine is your environment. When you are running heavy workloads directly on your primary workstation, a rogue command is a fatal blow. If your development environment isn't safe from the agent you are building, the speed of your inference simply does not matter. This brings us to OpenClaw. It is a highly capable personal AI agent that runs directly on your host machine. It connects straight to your local model and operates with virtually zero latency. But it also has absolutely no safety net. If an OpenClaw tool call tells your system to delete a directory, that directory is immediately deleted. Then there is NemoClaw. Under the hood, it is the exact same OpenClaw agent, but NVIDIA wrapped it inside a robust containment model, surrounding the agent with a Docker-hosted mini-cluster, strict network namespaces, and a dedicated authentication proxy. The prevailing theory among developers is that adding this much architectural indirection forces a heavy toll. All those routing hops and permission checks are assumed to cause massive processing delays, destroying the snappy responsiveness you expect from local AI. To find out exactly how much that security costs, I ran both frameworks side by side on the same DGX Spark, pointing them at the same massive 123 billion parameter Nematron model. We are directly testing the price of containment. Let's see if the safety of a sandboxed agent actually makes it too slow to use. And if you want to see more deep dive hardware tests like this, make sure to hit subscribe. Before initiating any downloads, I took an hour to build a Claude code skill using NemoClaw's official documentation. I essentially turned the manuals into an automated pre-flight checklist. This step scans the system snapshot against the documentation. Long before an install could fail, the skill proactively flagged a required namespace adjustment and caught a severe port collision. It saved hours of debugging by identifying the traps before they triggered. Now, let's look at the baseline. This chart tracks the time it takes the models to return a steady-state response. The raw Llama model returned an answer in exactly 26 seconds. The NemoClaw Sandbox took 52 seconds. It adds exactly 26 seconds of overhead, doubling the processing time per turn. On paper, this validates that heavy security wrappers cripple performance. But when I tested the host Llama, the one that is supposed to be raw and fast, it completely failed to provide an answer. Instead, it stalled out. The unprotected host agent refuses to do any actual work until it completes a lengthy, multi-turn onboarding dialogue. It insists on collecting your name, your pronouns, and time zone for a user profile, and each of those back-and-forth turns requires a full, heavy round of inference to process before moving forward. NemoClaw, however, handled all of this formatting during its 28-minute installation wizard. It prepaid that massive onboarding tax by populating the required configuration files right into the container image, bypassing the interview entirely. To find the source of that 26-second sandbox tax, I isolated the inference hop with a direct curl test. The authentication proxy only added about 30 milliseconds of delay. This proves the network isn't the bottleneck. The real cost comes from the internal agent loop and minor version differences between the host and the container image. Once the host agent finishes its tedious setup routine, it will process individual prompts faster. But on a fresh installation, the Sandbox NemoClaw easily beats the raw host in the race to provide your very first useful answer. For a solo developer, you have to look at the math differently. An extra 26-second wait per query is a cheap price for a sealed blast radius that guarantees your files remain untouched. Here is the default rule. For risky tasks, like running shell commands or untested tool calls, do it inside the NemoClaw sandbox. Only run the host OpenClaw for trusted daily tasks where the AI explicitly needs deep access to your actual directories. By running both versions on the exact same high-end workstation, you isolate your exploratory risks in the container and keep your verified operations running natively.
You get rapid iteration without gambling your actual working environment. True operational speed is measured in the absence of friction and the prevention of catastrophic errors. Next time, we'll push this sandbox through a heavy multi-turn benchmark to see if that penalty holds up under serious strain. Make sure you are subscribed so you don't miss it.